By 1909, Robert Millikan was able to determine the charge on an electron by studying the behavior of charged oil drops. He used an apparatus very similar to this. So I want to explain the apparatus. He took a battery, and a battery always has a positive and negative terminal. He connected the positive terminal to a metal plate. He also connected the negative terminal to a metal plate as well. So the positive side created a positive metal plate. The negative created a negative metal plate. He then took like a spray bottle, we call it an atomizer, and he sprayed in mists of water. The problem with water was it evaporated. So then he actually switched it to oil. So he sprayed in little oil droplets. And as the oil droplets moved through the air, they either gained or lost electrons. They became charged. So when we gain and lose electrons, that's called charging an object. And he would manipulate the battery by turning it up a little more power or turning it down a little less power until he can actually control the movement of the oil drop. So initially when he sprayed it, some would move towards the positive plate, some would move towards the negative plate, depending on if they gained or lost electrons. And he would play with the power until he could just suspend it, where he had enough positive or negative to make it just suspend. He recorded that value, how much voltage it took to suspend a specific oil droplet. Then what he did was he killed the power. So he turns the power off completely, and he timed how long it took it to fall a certain distance. So using the acceleration of gravity, our acceleration formulas, and using the charge on the battery, he was able to calculate different charges. And he got all kinds of different numbers. But one thing that they all had in common was that they're all a ratio of each other. They were all a ratio of 1.6 times 10 to the negative 19 coulombs. So some were 3.2, for instance. So it was 2 electrons. And what he determined was that if they're all a ratio of this, and this was the smallest number that he found, this must be the charge on 1 electron. And when it was double this, well, that meant there was 2 electrons. When it was triple this, 3 electrons. When it was 10 times, it meant it gained or lost 10 electrons. The units for charge is coulombs, named after Charles Coulomb. So charge is measured in coulombs, and the symbol for coulombs is capital C. He worked on this experiment for decades, absolutely decades, but an absolute genius to come up with the charge on a single electron before anyone could figure that out or even realize that they were able to measure it. To calculate that total charge on an object, we use this really simple formula. So Q is the symbol we use for the total charge. N is the number of electrons. Now, only the electrons can move in an atom. The protons stay put. So we've either gained electrons by becoming negatively charged, or we lose electrons, thus becoming positively charged. So N is the number of electrons, Q is the total charge, and E is the charge on 1 electron. And we know from earlier in the note, the charge on 1 electron is 1.6 times 10 to the negative 19 coulombs. So the formula makes sense. For instance, if you have 2 electrons, well, it'll be 2 times 1.6 times 10 to the negative 19, and that'll give you the total charge. If you had 20 electrons, it would be 20 times 1.6 times 10 to the negative 19 coulombs to give us the total charge. Number 1. What is the charge on an object that has an excess of 6.25 times 10 to the 19 electrons? So first thing we do is write down the given information. So we're looking for charge. Charge is Q. Excess of electrons means I've gained that many electrons. So that's the number of electrons. So the number of electrons is 6.25 times 10 to the 19. I know one other thing. I know the charge on 1 electron is simply 1.6 times 10 to the negative 19 coulombs. Our formula for total charge is Q is equal to NE. So just plug it in. 6.25 times 10 to the 19 times the charge on 1 electron, which is 1.6 times 10 to the negative 19. And when you put that into your calculator, you actually get 10 coulombs. Charge is measured in coulombs. Part B. So we're still looking for the charge on the object, but this time as a deficiency. That means it lost 1.0 times 10 to the 8 electrons. And the formula is exactly the same. Doesn't matter if we gain electrons or lose electrons. So we're looking for the total charge Q. And this time, the number of electrons that moved was 1 times 10 to the 8. And E is a constant. It never changes. It's 1.6 times 10 to the negative 19 coulombs. We use the exact same formula we used before. We know that Q is equal to NE. So it's number of electrons times the charge on one electron. So it'll be 1 times 10 to the 8 times 1.6 times 10 to the negative 19. And when you put that in your calculator, you should get 1.6 times 10 to the negative 11 coulombs. Now we're going to try our last example. It says the polyethylene strip has a charge of negative 5.2 times 10 negative 7 coulombs. So this is my charge Q. So Q is equal to negative 5.2 times 10 to the negative 7 coulombs. The negative just means I gained electrons. So we ignore it because all the positive negative means is, did I gain the electrons or did I lose the electrons? We're looking for what excess number of electrons. We want to find out how many electrons are we actually talking about here. And then we always have E is 1.6 times 10 to the negative 19 coulombs. So the formula is the same as it's always been. We know that Q is equal to NE. But this time, I'm trying to get N all alone. So I'm going to divide both sides by E. E's cancel out. And I'm left with N is equal to Q over E. We're going to plug in our numbers. So 5.2 times 10 negative 7 divided by 1.6 times 10 to the negative 19. And we actually get 3.25 times 10 to the 12 electrons. I didn't put the negative in because all the negative tells me is like, did I gain electrons or do I lose electrons? It doesn't change the formula at all.